Vecturas, as they say in Spanish, they probably don't. Probably not. But they might. It sounds Spanish. All right. Vectors. So we're dealing with things like area, volume, temperature, and all that kind of stuff. There's one value. It's just like size. What we call our magnitude. Temperature is 72 degrees. There's no direction to it. It's just 72 degrees. It is a magnitude. It is one measure. However, in the world, there's lots of things that have multiple things you have to take into account for. Like when you are driving, typically speaking, you have to account for your speed or your velocity and the direction in which your vehicle is going. I hope for most of the time that you are aware of both of those things. That's where vectors come in. Vectors account for two different measurements at the same time. For example, consider you're hitting two softballs into the air. The softballs are going to each have two different velocities and two different angles of trajectory. So that's why we have two different vectors and where they're hit. One is hit higher and one is hit straighter. The length of the vector is really important to the vector because that's actually keeping track of our velocity. In this scenario, the harder you hit the baseball or the softball, the longer the vector is going to be. So a longer vector indicates a higher velocity. So that is why this one is longer. Maybe I'll do this. We'll go longer vector equals higher velocity. That length is called magnitude. The length of a vector is called your magnitude. So a vector has two things. It has a direction and it has magnitude. Don't get confused by the term magnitude. That just means length. It means the length of the line. In this class right now, it just means the length of the line, which if you're in physics will apply to more things like what your velocity is, and you can compare velocities and do other stuff. But right here, we're just dealing with, that's just our length of our line. All right, let's talk about some things for a vector. Let's start with notation. Notation. We're going to start with a vector. One way to name a vector is to have a start and end point, in which case we'd call this vector AB. We're going to treat it like a ray, because it really is just a ray. So you're basically just going to write ray AB, which actually means vector AB. And if you remember from a ray, the direction of the arrow matters. If you'd put that the opposite direction, that would mean that the arrow would have to go this way, and you're going in a completely different direction. The other way you can name it, and it's kind of hard to do without having like a computer or something like that, is a capital lowercase letter. What? Did I say a capital? I meant a bold.
Yeah, you're like a capital.
You just have to have a capital lowercase. What's confusing about a capital lowercase letter?
Like a small Q.
Yeah, you make a capital letter but small. No, it is a lowercase, but it's bolded. It's a bold-faced lowercase letter.
So how can we tell it's bold?
What was that?
You bold it, Rob. As he said before.
Oh, yeah, too many. That's why I just said bold. Actually, I said... Yeah. Anywho, so we could name this AB or we could name it R. And a lot of times we don't make it bold because it's really hard to make bold by hand, and it's hard to write boldface because boldface looks more like you put like a line on it and then it's boldface. But we're just going to stick with just a lowercase r. Boldface was developed before they had computers and stuff to show bold without having to shade stuff in.
Just put a square on it. That's the same thing as the AB.
Just write R. We're just going to write R. Knowing that in a book it would be bolded. All right, so that's the two ways to write it. Usually we don't use AB. Usually we just use a single letter, a single lowercase letter. The next thing I want to talk about is magnitude. Magnitude is just length when we're dealing with vectors. Magnitude, when I talk about magnitude, I'm just talking about what's the length of the vector. It applies to velocity, but once you know the length, then you know the velocity and stuff. But just think of it as length for right now. Well, with magnitude, since it's length, it can't be negative. It always has to be positive. So to write down our magnitude, you're going to actually use absolute value bars. Absolute value bars will stand for magnitude in these directions. So first let's just do this. Magnitude is this length right here. That's our magnitude. In this example, if I was trying to represent magnitude, I would just write absolute value bars, AB, or I'd write absolute value bars, R. So when dealing with vectors, absolute value bars mean your magnitude. All right, automatically. Stop.
When you're talking about a vector, you're talking about like a line going one way.
A line going one way, yes. Correct.
So it won't like land anywhere.
It won't land anywhere. It doesn't curve. It's just a straight line like these. It's just a completely straight line. It'll never curve. A vector is always going to go straight. The only time it can curve is if you had a vector field, but we're not going to get into that. And in fact, there's so many vectors out there. We're simplifying it just for the pre-calc right now. They're always going to be placed at the origin, but know that vectors can go anywhere on the x, y plane in any direction. But right now we're taking all of our vectors and we're placing it at our origin. Yes?
That arrow over AB, does it show like the rays going from A to B?
Yes.
Then why doesn't R have one? Or no?
Because R is just the name of it. You don't have to.
Oh, okay.
R for ray, yeah. It isn't, but it works. So you don't have to put an arrow on that one. All right, it just tells you to look at that R one. Okay. The next thing we're going to talk about is scalar multiplication. We're just going to breeze over it for right now. It's not going to be part of your homework, but you need to know it. We'll talk more about it on next Monday. So if you look at that drawing, we have two tugboats pulling whatever this is.
Money.
What is that?
Money. Anywho, this picture isn't showing the tugboat being connected to it. It's showing the vector. The vector is showing how many pounds it's exerting on that particular barge. So if we look at A, A's vector is much shorter than 2A's, because 2 times A is definitely bigger than regular A. The longer the vector is, the more pounds are being exerted on that barge. So this one's definitely more than this one. And since it's 2A, it's exactly twice as much. So if barge or tugboat, the bottom one is pulling at 2,000 pounds, and the top one is exerting 4,000 pounds. It's twice as much. The length is twice as long, and we see it's A and 2A. So that is how scalar multiplication works with vectors. So first of all, let's come up with a vector down here, not that big. Let's go like there. And we will call it AB. So this is vector AB. Now let me write on the left. If I had to draw 2AB, I would draw it in the exact same direction. I would just draw it twice as long. So same exact direction, arrow going exactly the same place, except now it's twice as long. We would have an AB, and we would have another AB. Half works the exact same way. You should have a vector that's half as long as AB. So we could have half AB which will draw one about half the size of AB. Sure, that works. So that's half our size of AB. The last one we're going to talk about is negative AB. This is really the one I care about today because we're going to be adding and subtracting. So this is really one I want to get to. Negative just makes it go in the opposite direction. It's the same length, it's just going in the opposite direction. So if we picture this red tugboat, if I put the arrow the opposite direction, it would now be pushing the barge instead of pulling the barge. But the line's going to stay the exact same length. And it's going to look something like that. Except now A is down here and B would be up there. Yeah, Russ. It would be equal to... Yes, that would be. All right, but that's scalar multiplication. Like I said, we're going to talk more about that on Monday when we're doing the actual math behind it. I really just needed to get to that negative one because we're going to start adding and subtracting vectors right off the bat. Okay, Pasa.
When do you change the direction of the arrow?
Are you saying over the AB? The only time you would change it is if you wrote it out of order. So the traditional way is to have your arrow always going to the right.
Oh.
So you usually change your letters to write it. But let's say I didn't want to write BA here. You could still keep it AB and just change your arrow direction. But traditionally, you always keep it going to the right. You usually let the letters change. Because the more standard we are, the quicker I can read problems and stuff. I don't have to look at the arrows as much. If I know that most of them are going to the right, I'm not going to spend a whole bunch of time looking at the arrows of the vectors. All right, any other questions? Cool. All right. Adding or subtracting vectors. This is the visual adding and subtracting. On Monday, we'll talk about actually doing the algebra adding and subtracting. So let's call, for the sake of this, let's call the bottom one A and the one to the right or left B. That's my vector A, my vector B. Now note, these are just two individual vectors. These are two individual vectors. A is all by itself, B is all by itself. We just moved them so their tails are together. All right, the first thing we're going to do is we're going to do A plus B. What happens with A plus B is we run all the way through the distance of A. And then what we're going to do is we're going to take B, copy and paste it right on the end of A. It'll look something like this. Where I tack B onto the end of A. I'm just copying B and pasting it right here. And then we're going to go from where the tails intersect all the way to that arrow ends, and we're going to put an arrow up there. That black line right there is now A plus B. Now, if I need to do B plus A, that means I would run up B. First, I'd probably label them. I'm going to label them the exact same with B and A. We would run all the way up B, and then we paste A onto it. So it looks something like this. Right at the end of B, we'd paste A onto it. Once again, we go from where the tails intersect, put an arrow, and that is now B plus A. Nope, B plus A is the exact same value as A plus B. It comes up with the exact same vector. Adding vectors, no matter which one you do first or second, is always going to result the same because that's what addition is. 2 plus 3 is the same thing as 3 plus 2. The real problem comes in with subtraction. You have to do it in the proper order for subtraction because 2 minus 3 is different than 3 minus 2. So make sure you do things in order and you read it correctly. So if this is B and this is A, we're going to do B minus A. Here's where that negative comes important. Negative means this length is going to stay the same, but it's going to go the opposite direction. So if A goes that direction, Negative A is going to go the other direction. So we're going to run up B, and then we're going to attach A to it going the opposite direction. So that right there is negative A. Now we're going to go from where those two vectors intersected at their bases, draw a line, and this is now B minus A. Let's attach one more to it. Let's do A minus B so we can see it's different. A minus B would be you run out A, and you go in the opposite direction, so I'd have to lean in. All right, B would go like this, so the opposite would go kind of in like that. So our negative B would look something like this. And this would be A minus B. Note they'd create a straight line if done 100% perfect, running in two different directions. So B minus A and A minus B are just opposites of each other. Kind of like 3 minus 2 is just an opposite of 2 minus 3. Works the same for vectors. It's just lengths. We're just dealing with lengths here. Yeah, Ross.
So there's no like actual math. Like doing
I know what you mean. There will be, on Monday, we'll put numbers to these things. Like what it means when I add. So we'll have like B is this vector and A is this vector. Now subtract and we can see the numbers. But right now it's all visual math.
yeah, okay.
It's just visual math.
Yeah.
But I knew what you meant. I knew what you meant.
Yeah.
All right, guys. The next thing we're going to work on is horizontal and vertical components. Horizontal and vertical components. We're putting a lot of words to things that we already know exist. Your vertical and horizontal components. A vector W moves in two directions. Horizontally, W sub x, and vertically, W sub y. But so has everything you've ever put on an xy plane. A point always has an x value and a y value. Your x value is always your horizontal. It's left or right. Like if you have to plot the point 3, 4. You go right 3, up 4, and that'll be your point. X values are your left, right. Y values are up, down. I'm not changing anything. We're just changing the words that are assigned to it because we're dealing with vectors. All right, so these words, okay, specifically deal with vectors. But I'll try to make it as applied as we can. Horizontally, W sub x, still just our x values. Vertically, W sub y, still just our y values. All right, so we have this vector W. The first thing we need to recognize, when we're dealing with vectors, this is its name. W is not its length. W is its name. So we're going to pick a letter to stand for our magnitude. And I'm going to pick R. We're going to let R equal absolute value of W. Absolute value of W stands for the magnitude. In other words, what's the length of that line? And then I'm going to put that on the picture real quick, that R is our magnitude, which means R is that length. It'd be the number, 4. Maybe it's 4 units long. And like I said, all our vectors are going to start at 0, 0 in this class right now. So we don't have to worry about it being in other places. Well, this is our horizontal component. This is our vertical component. Yeah?
Is it Wx plus Wy?
Is that the length of it? I don't know what your answer.
Yeah.
I guess I didn't ask the question. No, are you saying like Wx plus Wy equals W?
You asked what the length was, and he answered.
Oh, yeah, that's what I was just saying. Is that...
Yeah.
Oh, okay. I guess mine was more of a rhetorical question right now.
Sorry.
No, that's fine.
I understand.
what I'm going to do to get that length, is I'm going to treat this as a right triangle, where this is the base of my right triangle, and this is my height of my right triangle. It's just like when you normally put a point on an XY plane. We did like our distance formula and stuff. All right. So we have a right triangle now. We have a right triangle, and I'm going to call this alpha down here. Down at bottom left, I'm going to call that my alpha. Well, the reason why we're going to...
That's a thing.
Oh, I'm sorry, theta. All right, we're going to start with cosine. We're going to say cosine theta. Cosine theta, cosine SOHCAHTOA, is adjacent over hypotenuse. Well, our adjacent right now is W sub x over our hypotenuse, which is our length of our hypotenuse. Therefore, if I'm talking about component form, component is our W sub x. Our W sub x is going to equal r times the cosine of theta. In other words, our horizontal is going to equal the length of the radius, or length of our vector, times cosine theta, whatever angle they give you. So that is our component form. Horizontal movement equals r times cosine theta, where r is the length of our vector. And theta is just going to be an angle that's given to us or something we can find. Well, if that's our cosine, if I'm dealing with sine of theta, that's going to equal my vertical, W sub y over r. Well, that means W sub y is going to equal r times sine of theta. But once again, that just deals with right triangles, where W sub y is my vertical. Component. Any questions on vertical and horizontal components? The last thing we're talking about, I'm going to put another slide, is what if I ask for the magnitude of those? It just means take the absolute. Magnitude just means take the absolute of whatever value you got. Because magnitude is distance then, and distance is always positive. These will not always be positive. Just like if I put a point down here in my fourth quadrant. Our x value is positive, but our y value would be negative. That's what you'd get out here. But if I ask for a magnitude, say I ask for the magnitude of your horizontal, that would just be, well, r times cosine theta, but we put absolute value bars around it to make sure it's positive. Just like W sub y, if I wanted the absolute value of that, I would just put absolute value bars around that and say r times sine of theta. And that just is our magnitude of our vertical, and that's our magnitude of our horizontal. So you have to be very careful of what the question's asking you. If it's asking for a magnitude, you need absolute value bars. If I just ask for the components, no absolute value bars. All right, let us do an example. So it says find the magnitude. Magnitude means I need positive absolute value bars of the horizontal and vertical components for a vector v with magnitude 8.3 and a direction angle 121.3 degrees. So what we're talking about is a vector at 121 degrees, which might be somewhere over here, where this measure here is 121.3 degrees. And the actual length of this line is 8.3 units long. I want to know how far left does it move and how far up does it move, or if I could place those points on an x, y, that we could have that point. But I don't want positives and I don't want negatives, I just want positives. So since it's magnitude, we're going to do the absolute value of our w sub x. Well, our horizontal is r times the cosine of theta, where r is the length of our vector. So in this case, it's going to be the absolute value of 8.3 times the cosine of our theta. Our theta is always going to be our directional angle. So that is going to be 121.3 degrees. Our vertical, and what I usually do just to save me some time, I usually type in my vertical and my horizontal right away, and then I can type in my calculator at the same time. Yeah?
Why isn't it 121.3 minus 90? Because, like, aren't we... Because, like, that's a rectangle.
Uh-huh. You could.
Like, up it.
Yeah, no, you
come
could.
out with the same
It would come with the same thing. It works with the unit circle. It's just easier to not have to do that.
Yeah, okay. I didn't...
No, but based upon our unit circle, we come up with the exact same values because they repeat, right? But you are 100% correct. Especially when we're taking the absolute value, I don't have to worry. I can either find that little angle there. In fact, you could do this little angle here. But something that's just easier, just to, if I can use the angle they gave me, why not just use that angle? But it was some good thought. All right, so we're going to do 8.3 times the sine of 121.3 degrees. And I usually write them both out, and then I plug in my calculator so I don't make mistakes along the way. Our horizontal component should be about 4.3. Is that what people got? And our vertical should be about 19.3.
I got 7.1.
Oh, I got 7.1.
Why did you say 15?
I read it wrong.
Okay.
No, I'm just kidding. I wanted to hear the panic in everyone's voices. I feed off that. No, it should be about 7.1. It's about 7.1. And since it's magnitude, it has to be positive. Because if you'd right now type in 8.3 times the cosine of 121.3 degrees, you'd come up with a negative 4.3. But it wanted the distance, so you have to put it as 4.3. What this means right now is this x value would be right here at 4.3 away from the origin. And then the height would be 7.1. That's all this is saying. That's all our horizontal and vertical components are saying, that this distance here is 4.1 and the distance up is 7.1. Since it's magnitude, you can't put a negative on it. So rather than be negative 4.2, it's a positive. All right, that is component. That is how you find the magnitude of our component. All right, let's talk a little bit more about component form. As I illustrated here, and as I talked about here, our components are really our x and y values. So when we're talking about component form, it's not a surprise that we kind of deal with them like x and y values. In fact, we write it almost like x and y values. This point, normally we'd say it's like 3, 2, it's our x and y values. For vectors, we're going to call it a, b instead of x, y. That's a g. A, b. And instead of parentheses, crazy, because they're vectors, and vectors get their own special symbols. But do not confuse the words of vectors and normal stuff. That is just a normal x and y value. This is our distance this way. A is kind of like our x values, and b is our height. But you should really be thinking, until you get really good at this, just think x, y values. It's just a point. It's a point on an xy plane that we just have to find those values of. All right, so component form uses the terminal point. That is point A comma B. That is where that terminates. Magnitude. Notice the vector creates a right triangle where the magnitude is the hypotenuse. So we're going to let R stand for our magnitude again. And then we're going to once again kind of picture this as a right triangle where A is the base and B is the other side. Well, if I'm talking about R and I have a right triangle, anytime I have a right triangle where I know all three sides, you should kind of immediately think A squared plus B squared equals C squared. You got it. In this case, we don't have C squared, we have R squared. But you could make it C squared, I don't care. Equals A squared plus B squared. And we could use that formula to solve for the length of our vector. In other words, R equals, normally it's positive or negative, but our length of our vector has to be positive, so it would just be strictly positive square root of A squared plus B squared. That is not really a question yet. Guys, there's lots of formulas to this stuff. The quicker you're at realizing it's just a triangle and you can derive all this stuff on your own, the better you are than just memorizing stuff. But you can memorize these things and not know where they come from and just plug and chug. But if you understand where they come from, then it's a lot less memorizing. All right, let's go through some examples. It says find the magnitude. Magnitude is the length of the vector. Length of the vector is right here. Yeah.
Is it plus minus?
No. It is just plus because length of the vector has to be positive. Length of a vector has this equation. All right. So let's look at this awesome guy here. All right. So first of all, let's make a right triangle. And we're always going to make our right triangle by connecting our terminal end to the x-axis. So you'll either be going up or down always to create your right triangle. So our right triangle is going to look something like that, where our base is that -2, and kind of that height of it is going to be our -5. Now I have a right triangle where I know the two sides. You didn't have to memorize the formula to know I'm trying to get this length is my magnitude. My magnitude is just this length. It's A squared plus B squared equals C squared. You don't need to memorize a brand new formula. So to find my magnitude, we're just using A squared plus B squared equals C squared. But in this case, I'm going to let R stand for my hypotenuse. So we're going to have R equals the square root of A squared. Let's make our A that -2. Plus our B squared, which is -5 squared. Well, that's just 4 plus 25, which is square root of 29. I'm not going to simplify it further than that. So we don't need a calculator. It's just square root of 29. So this distance right here is the square root of 29. It also says I need to get the directional angle. The directional angle, just like the unit circle, is how big is this angle from the bottom of quadrant 1. So I'm looking for this angle here. I'm going to call that theta. And hopefully I actually draw theta and I don't draw alpha this time. Nope, I got theta. Well, I can't jump straight to theta in this one. I do know that from here to here is 180 degrees. I don't need to solve that. That's 180 degrees. The only thing I really need to figure out is, what is this little distance here? And that little distance there, I'm going to go ahead and call beta. I'm going to call this distance beta. Well, that means alpha, or theta, next time up today, is 180 plus whatever my beta is. So let's find beta. Now, we know all three sides. So I could use sine, I could use cosine, I could use tangent, I could use cosecant, I could use probably don't go that far. I'm going to go ahead and just assume that there's a chance I made a mistake here. And I'm going to use the two values they gave me. They gave me -2 and -5. Those are two sides. So I'm going to use tangent. I'm going to use tangent because they gave me those two values. And we're going to say tangent of beta in this case is going to, tangent is TOA, which is opposite over adjacent. So that'd be -5 over -2. What's really cool about using tangent, it will always be your b value over your a value. If you get good at this, it just is that value over that value every single time. Well, I don't care what tangent beta equals. I care what beta equals. So that means I need to take the tan inverse of both sides, which means I'm going to have tan inverse of a +5 over 2. And that we should come up with about 68.2 degrees. Now just a reminder, that is not my directional angle. That full theta is my directional angle. That is going to be my directional angle. Well, our directional angle is just 180 degrees plus that 68.2 degrees. Which is going to equal 248.2 degrees. Now I have my magnitude, and I have my directional angle, and really I did nothing new today. I used a squared plus b squared equals c squared, and I used tangent. That's all I used today. There was nothing new. We're just having new terms that go with draw a straight line from the origin a certain direction. Any questions on this? Okay, we have one more example. It says find the component form for the vector of magnitude 40 miles per hour with directional angle 330 degrees. Once again, the word I'm looking out for is magnitude. Magnitude says take the absolute value. This problem does not say magnitude in it. So since it doesn't say magnitude, I'm really just finding that a value and that b value. My a value should be positive. My b value should be negative because I'm going down in the negative direction. So it's just regular component form. It's not magnitudes. All right, regular component form. It's going to be the same thing, though, without absolute value bars. Our w sub x, or our x value, is going to be our magnitude, or the length of the line. In this case, it's 40 miles per hour. It's still just 40. Times our cosine of our angle, which is 330 degrees. You could also do the 30-degree one, as long as you recognize which needs to be positive and which needs to be negative. Yes, Safa.
Wait, so you could do the thing where you draw the line up and then just use the 30, 60, 90 triangle to solve it?
Yeah. Yeah. Yep, you could. Because you know the hypotenuse, and you know this angle. You just have to make sure you have this one would be your negative, and this would be your positive. As long as you keep all that stuff track, boom, right triangle, solve it. And that's in short what we're doing. Yeah. Because you'd use the cosine of 30 degrees. We're just using the cosine of 330 degrees. All right, but that should equal 40 times the cosine of 330 degrees. Oh, I don't need this, because I didn't actually do it on here. I'm going to go down here. Is 40 times the cosine of 330 degrees, the same thing as cosine of 30 degrees. So that's going to be the cosine of square root of 3 over, nope, go back. It's just times square root of 3 over 2, which is going to equal just 20 square root of 3. Our y value, or our vertical, would be 40 times the sine of 330 degrees. which equals 40 times, with that square root of 3 over 2, then sine of 330 is 1/2, which is going to equal 20. Now, I want to note, if it asks for component form, you do have to put it in component form. So that means we're going to put a little arrowheads, and we're going to put 20 square root of 3, comma, 20, and that is our actual answer. Natasha. Boom. That's why we do that check, right? Yeah. We should do a check that says one of those needs to be negative. So no matter what I do, if I make any mistakes, I should have had that redundant check saying, well, I know it should have been positive going right. My x value is positive. Going down, it should be up. It should have been negative 20, which means it really should have been negative 1/2. As long as you do those checks, it doesn't matter if you're using 30 degrees or 330 degrees. You will get it right every single time as long as you recognize what's happening. That's why Safa's question was so great. Can you just draw a triangle? Can you just draw a triangle here and use this as my theta, which would be 30 degrees, and know that this is my A and B, and say, well, okay, cosine of 30 degrees is adjacent over hypotenuse. We'd have the same answer. I can do sine of 30 is opposite over hypotenuse, which should be the same answer as long as I recognize that it needs to be negative at the end. The quicker you recognize these are triangles, the easier it becomes. Yeah, Mary?
So for the notation stuff, you don't want it to be decimals?
If it's on the unit circle, I do want you to keep it as exact values.
Okay.
Because on a test, that's what I would do. I would say find the exact values. And I did that on the test recently because one of your triangles was a degree that was on the unit circle. And they were supposed to be equal. It was supposed to be one right triangle. And some people missed that because they just plugged in their calculator and rounded. If it's on the unit circle, leave those values as exact as you can. All right, guys, this homework.